Hello everyone, and welcome to another video on our own devices. I'm Jean Messier, and today we are having a look at what is effectively a 2.5 millennium old practical joke. This is what is known as a Pythagorean cup, and as the name implies, the invention of this cup is typically attributed to Pythagoras of Samos, the 6th century B.C. Greek mathematician, probably best known as the namesake of the Pythagorean theorem in geometry. Now, in addition to being a mathematician, Pythagoras is also a philosopher, and he ran a school of philosophy, called by some a cult, in Crotona, in southern Italy. And among the many tenets of this philosophy was an emphasis on moderation in all things. And according to legend, Pythagoras invented this cup in order to teach that lesson. So how this works, that if you look inside the cup, you'll see that there is a line scribed on the inside wall. And if I fill up the cup to that line, it works like a regular cup. I can drink out of it normally. However, if I fill the cup above that line, then all the contents drain out through a hole in the bottom. And if you imagine the cup being full of, say, red wine as opposed to water and the tremendous mess that would make, you can see that this provides a very dramatic demonstration of why it doesn't pay to be greedy. And indeed, this type of cup is also sometimes known as a greedy cup. Now, while we don't actually know for sure whether Pythagoras actually invented this cup, vessels of this kind continued to be very popular for many centuries after his death. For example, in 2012, archaeologists excavating around Vinkovci in modern-day Croatia uncovered a Roman version of the Pythagorean cup dating from the 4th century AD, with a little bit of a twist, which was a little sculpture of the mythological figure of Tantalus. Now, if you're not familiar with this myth, Tantalus tried to argue against the omniscience of the Olympian gods, and for this he was punished by being thrown down into Tartarus, the deepest part of Hades. And there he found that if he reached to the waters at his feet in order to drink, the waters would recede. If he reached up to the fruit hanging from the branches above him, those would also recede out of reach. And this is where we get the modern term to tantalize. Right, so let's have a closer look at how the Pythagorean cup is constructed and how it actually works. So if you look inside, you'll notice that there is this little truncated cone or spike on the inside with a couple of holes at the bottom. Now this is hollow, and inside is another concentric truncated cone with an open top. And the channel on the inside of that inner cone is connected to a channel that runs through the stem of the cup and out through a hole in the bottom. So when you fill the cup up to the line, the water level in that annular space between the two cones is going to rise at the same rate. This is Pascal's principle of communicating vessels. However, when you fill above the line, that water is going to spill over into that inner channel, is going to create a siphon, which then drains all the contents of the cup out through the central channel. Now, a siphon is a very simple mechanism used to drain fluid from one container at one elevation to another container at a lower elevation while passing through a higher elevation in between. And these have been known about and used for thousands of years. The ancient Egyptians used siphons to raise water from rivers into irrigation canals and in wine and beer making. And indeed, if you make wine or beer at home, you've probably used a siphon to transfer out the wine or beer from the fermentation vessel while leaving the lees or the sediments behind. The ancient Romans used inverted siphons to transfer water across valleys that were too wide or deep to build a traditional aqueduct, and you yourself may have used a siphon many times in your everyday life. For example, if you own an aquarium, you've probably used a siphon like this in order to clean the gravel at the bottom and transfer out water when doing a water change. If you've ever had to transfer gasoline from one vehicle fuel tank to another, I won't ask why, then you've probably also used a siphon. And funnily enough, this is one of the proposed origins for that perennial Canadian insult of hoser. And even this morning, if you went to the washroom, you used a siphon. So the S-bend in a traditional toilet acts as a water trap. It has a small amount of water in it that prevents smells from backing up through the sewers. But when you flush the toilet, water is released from the tank into the bowl, causing the water level to rise. And eventually that causes water to spill over the other side of the S-band, completing the siphon and causing the contents of the bowl to be drained out. And there are many other examples that I'm sure that you can name. Now, since siphons have been around for a very long time and are very simple devices, basically just a curved tube, this must mean that the physics behind their operation are very well known by now, right? Well, actually, no. Strangely enough, the operation of a siphon is a lot more mysterious and complicated than you might think, and is the subject of considerable scientific debate to this day. And this is what I want to talk about today. Now, despite the fact that we've been using siphons for thousands of years, scientists really didn't start investigating their inner workings until around the 16th century. And one of the first scientists to propose a theory of operation for siphons was Galileo Galilei, and he proposed that they worked via the principle of horror vacui, or nature abhors a vacuum, which is an outdated scientific principle going back all the way to Aristotle. And so according to Galileo, as gravity pulls the fluid down the descending leg of the siphon, this creates a low pressure, and since nature will try to fill any vacuum that tries to form, this causes fluid in the ascending leg to rush up to fill that void. Now, although Galileo was using some outdated terminology and principles here, as we'll see later on, he was actually very close to getting the right answer. Now, shortly after Galileo's time, some groundbreaking studies were conducted on the nature of pressure and vacuums by a pair of scientists, Evangelista Torricelli in Italy and Blaise Pascal in France. And what Torricelli did was to fill a long glass tube closed at one end with mercury and invert it into a larger dish containing more mercury. And what he found was that the column of mercury dropped a certain amount and then stopped. Now, since there wasn't any way for air or any other gas to get into that space at the top of the column, Torricelli realized that it must contain a perfect vacuum, or as nearly perfect as he could create. There would be a little bit of mercury vapor in there. And so he had disproved horror vacui, because if that were true, that would mean that the suction of the vacuum would have pulled the mercury all the way up into the column. Rather, he realized that what was holding the column up was not the vacuum sucking it up, but rather the atmospheric pressure pushing on the surface of the mercury in the dish and holding the column up. And the height of this column depended not only on the ambient atmospheric pressure, but also the density of the fluid being used. So this was around 76 centimeters for mercury at sea level. But if you repeated the experiment with water, for example, then you could support a column around 10 meters high. Now, in another famous experiment, Blaise Pascal climbed a mountain carrying this apparatus. He found that the higher he went, the lower the atmospheric pressure and the lower the column of mercury that it could support. So Torricelli had effectively invented the mercury barometer, a device used to measure atmospheric pressure and predict the weather, which is why today 2 units of pressure, the torr and the Pascal, are named in their honor. Now, Pascal conducted a number of experiments on siphons in which he made an important discovery, which was that the maximum height to which you can build a siphon is identical to the barometric height of whatever fluid you're using. So say 10 meters for water, 76 centimeters for mercury. And based on this result, he postulated that siphons work not by horror vacui, as Galileo had proposed, but rather via atmospheric pressure. So, as Galileo had described, as gravity pulls the fluid down the descending leg, it does produce a negative pressure. But what causes the rest of the fluid to rush up the ascending leg is not horror vacui, this void that nature cannot abide by, but rather atmospheric pressure pushing down on the surface of the reservoir and thus pushing the fluid up into the siphon. And this would remain the standard explanation for the operation of siphons for many centuries. However, the thing about theories, at least good theories, is that they have to make testable predictions. And if the atmospheric pressure theory of this operation of siphons is correct, this means that a siphon shouldn't operate in a vacuum. After all, there is no atmospheric pressure to push the fluid through the siphon. But here's the thing. Siphons absolutely do work in a vacuum, as experiments using both mercury and a specific type of liquid called an ionic liquid have shown. And ionic liquids are liquids where the molecules are held together by ionic bonds. And these bonds are so strong that the liquid basically can't evaporate. So if you put them in a vacuum, you're not going to get even a little bit of vapor inside the chamber. It is going to be a hard vacuum. And I will link to a short video on another channel showing this exact experiment. But as you can see in this footage here, even in a hard vacuum, a siphon absolutely will work. And so this seems to throw out the window the notion that atmospheric pressure is necessary for the operation of a siphon. So what's happening here? How does a siphon actually work? Well, in addition to the atmospheric pressure model, there is an alternate theory as to how siphons work. This is known as the molecular cohesion, or sometimes the chain theory. And the idea here is that the fluid going through the siphon is modeled like a chain going over a pulley, where as gravity pulls the fluid down the descending leg, the intermolecular forces within the fluid pulls the fluid up over the apex of the siphon and down into the descending leg. Now, at first glance, this theory seems very promising, neatly explaining how a siphon can operate both under regular atmospheric pressure and in a vacuum. But again, good theories make testable predictions. And to see how well the cohesion or chain model holds up, let's have a look at a series of experiments conducted in 2011 by Alex Richard and P.N. Binder of the University of Hawaii. Now, these experiments were conducted in response to an article by Dr. Stephen Hughes of Queensland University in Australia, where he claimed that the traditional atmospheric pressure explanation for siphons, which had been in textbooks and encyclopedias for centuries, was in fact wrong, and that the operation of siphons was actually better explained by the chain or cohesion model. So the apparatus used by Richard and Binder was really quite simple, consisting of just a 2-liter soda bottle as the reservoir and a piece of clear, flexible plastic tubing as the siphon. And they used this to conduct 4 different experiments. So in the first experiment, they installed a valve at the apex of the siphon so that the siphon could be exposed to atmosphere when the valve was open. So with the valve closed, they primed and started the siphon flowing, and then once it had gotten started, they then opened the valve to atmosphere. So if the cohesion or chain model is correct, this shouldn't do anything, since it's the cohesion between the molecules of the fluid that drag the fluid up over the siphon and not atmospheric pressure. But in reality, that's not what happened. When they opened the valve, the siphon broke, and the fluid drained out through both legs. Now, in the second experiment, they installed a valve in the middle of the siphon such that they could fill the descending leg of the siphon with fluid, yet leave the ascending leg empty. They then opened the valve. Now, if the cohesion theory is correct, then the fluid should just run down the descending leg and nothing else should happen, since there is no direct connection between the fluid in the descending leg and the fluid in the reservoir. But once again, that's not what happened. When they opened up the valve, the fluid did descend the descending leg, but it also drew fluid up the ascending leg, which once it cleared the apex, started the siphon flowing again. Now, in the third experiment that they did, rather than just having the ascending leg of the siphon loosely fit through the neck of the bottle, they instead sealed it to the cap and sealed the cap to the bottle, stopping any air from flowing into the reservoir. And so if the fluid cohesion theory is correct, then the siphon should draw all of the fluid out of the bottle, causing the bottle to be evacuated and collapse in on itself. Atmospheric pressure should have no influence on how much of the fluid leaves the reservoir. But yet again, that's not what happened. Instead, the fluid flowed through the siphon for a certain amount of time, and then once the pressure inside and outside the bottle reached equilibrium, the siphon stopped flowing. And then finally, we get to the fourth experiment, in which they made the ascending leg of the siphon longer than the descending leg, but made sure that the fluid level in the reservoir was always higher than at the outlet. Now, again, if the fluid cohesion theory is correct, the greater volume and thus greater weight of fluid in the ascending leg should make the siphon flow backwards, since that is what's drawing the fluid through the tube. But nope, the siphon flowed just as it normally would. And indeed, there are a number of other experiments that can be conducted that show that the fluid cohesion model is seriously flawed. For example, if that theory were correct, then a siphon like this, also known as a hero siphon after the Greek engineer Hero of Alexandria, wouldn't work, since there is a lot more volume and thus weight of fluid in the ascending leg than there is in the descending leg. Yet, those of you who own aquariums know these work just fine. Siphons also work very well, even if they're full of bubbles, even though there's no direct connection between the fluid molecules in each segment between the bubbles. You could also create what's known as a flying drop siphon, where rather than having a direct connection between the ascending and descending legs, the fluid going up the ascending leg sprays out into space and is broken up into little droplets, which then drop into a reservoir connected to the descending leg. Furthermore, you can actually siphon gases, particularly denser gases like carbon dioxide, just as you would a liquid, despite the fact that the forces between the molecules of such gases are very weak. So, what's going on here? Most of the experiments that you can conduct using siphons demonstrate that the molecular cohesion or chain theory is incorrect, whereas the fact that a siphon will operate in a vacuum demonstrates that the atmospheric pressure theory is incorrect. So, which is it? How does a siphon actually operate? Well, to shed some light on this apparent contradiction, let's have a look at an experiment conducted in 2015 by A. Boatwright et al., in which the team was able to construct a water siphon 24 meters in height, which is nearly 2.5 times the regular barometric height of water. And they were able to accomplish this by first degassing the water before pouring it into the siphon, by which I mean they expose the water to a vacuum in order to cause all of the dissolved gases and other impurities to bubble out, leaving extremely pure water. But how does that work? How does using extremely pure degassed water allow you to build a siphon much taller than the barometric height of said water? Well, to understand this, we need to understand what is responsible for the barometric height of a fluid in the first place. So the barometric height is not only the maximum height to which you can build a barometer using a particular fluid, it's also the maximum height to which you can raise that fluid using a simple suction pump, that is, by reducing the pressure above the fluid column. And how this works is that once you've removed a certain amount of air above the fluid column, you have reached the vapor pressure of that liquid, causing the liquid to start to bubble and release vapor into that evacuated space above it. And no matter how much of that vapor you remove, it will be replaced as the fluid boils. And so you will never be able to raise the fluid higher than that level using a vacuum pump. And this is exactly what happens in a very tall siphon. At a certain height, the sheer suction created by the fluid flowing through the descending leg drops the pressure in the water to a point where it starts to cavitate, that is, form bubbles of vapor. And if you have too many of these bubbles, this can break the siphon. However, the thing about bubbles is that they require a nucleation site. And indeed, if you pour yourself a glass of soda or champagne, you'll notice that the bubbles don't form just anywhere. They form at very specific points. This is typically a little speck of dirt or a stray fiber from the cloth that was used to dry the glass. And this is where the molecules of gas accumulate or nucleate and form bubbles that then peel away. However, if you remove as many impurities as possible, and thus the number of nucleation sites where cavitation bubbles can form, then you can drop the pressure of the liquid below the point at which it would normally start to cavitate. And this is what allows you to build a siphon that is so much higher than the barometric height of the fluid within it. It turns out that Blaise Pascal's key discovery that the barometric height and the maximum siphon height for any given fluid are identical was nothing more than a coincidence caused by the limitations of the materials he had available at the time. So, where does this leave us? What is the actual operating mechanism behind a siphon? Is it atmospheric pressure or is it molecular cohesion? Well, as it turns out, it's probably nothing more complicated than plain old pressure equilibrium. So, as gravity pulls the fluid down the descending leg of the siphon, it is going to create a reduced pressure in the fluid. And even if there isn't any atmospheric pressure to push more fluid in to fill that gap, the fluid will still flow in order to maintain the pressure equilibrium of the entire system, which you might recognize as being effectively the same explanation that Galileo Galilei gave, only using more modern terminology and scientific principles, as opposed to the outdated idea of horror vacui. So you know what? Good job, Galileo. I think that's worth drinking to. And so there you have it. A brief summary of the surprisingly complicated and controversial physics of the Hubble siphon, demonstrating that we don't need to delve into the realms of cosmology or quantum physics for nature to surprise us. Anyway, that's all I have for you today. Thank you so much for watching, and I'll see you next time where we'll look at yet more fascinating devices and hopefully scientific principles, just like this one. Until then, I'm Jean Messier from Our Own Devices. Have a great day.